Have you ever wondered why power lines don't just hang still? When electric current flows through parallel wires, they exert invisible magnetic forces on one another. Today, we will explore the physics behind this interaction and how to calculate the resulting force. The direction of the current determines the behavior of the wires. Currents flowing in the same direction attract each other, while currents flowing in opposite directions repel. This is a fundamental principle of electromagnetism that we see in high-power industrial equipment. To understand why this happens, we must look at the magnetic field. Wire 1 creates a circular magnetic field around itself. This field, which we call B1, reaches over to where wire 2 is located, influencing the charges moving within it. Using Ampere's law, we can calculate the strength of the magnetic field B1 at the position of the second wire. The field strength is directly proportional to the current and inversely proportional to the distance r separating the two conductors. We use the first right-hand rule to find the field direction. Point your thumb in the direction of the current, and your fingers curl in the direction of the magnetic field. This helps us visualize the circular paths of the magnetic flux. Once we know the magnetic field B1, we can find the force exerted on wire 2. The force is equal to the current in wire 2 multiplied by its length and the external magnetic field strength. This is known as the Lorentz force. To find the force direction, use the second right-hand rule. Point your fingers in the direction of the magnetic field and your thumb in the direction of the current. Your palm now pushes in the direction of the magnetic force. By combining our equations, we get the unified formula for force per unit length. This elegant equation shows that the force depends on the product of both currents and is inversely proportional to the distance between the wires. Wire 1 carries 10 amperes and wire 2 carries 20 amperes. We want to find the force exerted on every meter of these wires. First, we calculate the magnetic field produced by wire 1 at the location of wire 2. Plugging in our values, we find a magnetic field strength of 40 microteslas. This is the field that wire 2 feels. Now, we multiply this field by the current in wire 2. The resulting force is 0.0008 newtons per meter. Since the currents are flowing in the same direction, the wires will pull toward each other with this specific force. It is important to note that wire 2 exerts an equal and opposite force back on wire 1. This follows Newton's third law. The force calculation remains the same regardless of which wire you choose as the source of the field. The distance between wires is a critical factor. Because it is an inverse relationship, doubling the distance cuts the force in half. In high-voltage engineering, spacing is carefully calculated to prevent mechanical stress from these magnetic forces during power surges. To summarize, current creates a magnetic field, and that field exerts a force on nearby currents. Remember the direction rules: same direction attracts, opposite repels. The force grows with current strength but weakens as wires move apart. Let's test your knowledge. If we double the current in both wires simultaneously, how does the total force change? Think about the formula where we multiply I1 by I2. Take a moment to calculate the factor of change. The answer is quadrupled. Since the force is proportional to the product of both currents, doubling each one results in a force 4 times as strong. Thank you for joining this lesson. Generated by Vision Solve AI.